Welcome everyone to day 4 of the Global Quantum and AI Program 2024. We have an exciting session coming up today with William Oliver giving a keynote on quantum computing. William Oliver, professor at MIT, followed by a virtual lab tour in his lab at MIT, a Q&A with Shantanu, his PhD student, and Will Oliver. And then after a little break, we will continue with Grover's algorithm, part of Q-Bronze. It is an honor to introduce you, Will Oliver. Will Oliver is a professor at MIT, both a professor of electrical engineering and physics. He is the director of the Center of Quantum Engineering and an associate director of the Research Laboratory of Electronics at MIT. He won numerous prizes, including AAAS Fellow and a Fellow of the American Physical Society. To many of you, I don't need to introduce him because he is so well known and has paved the way for so many developments in quantum computing. I don't want to take any time away from you, Will, so without further ado, let's get started with your keynote, Introduction to Quantum Computing.
Oh, thanks, Marlou, for that very kind introduction, and it's such a pleasure to be here with Womanium and all the great work that you're all doing. And thank you for taking time out of your schedule to join me too. I'd like to talk at a high level about an introduction to quantum computing. Let me see if I can hide that thing. And yeah, well, let's just get into it. Yeah, so before we get into quantum computing, let's take a step back and remember that quantum technologies are broad. Quantum information covers sensing, it covers networking, and of course, it covers processing and computing. And we generally call this quantum 2.0. I'll explain what 1.0 was in just a minute. But this new quantum 2.0, if we had to give it a quick definition, I would say that it utilizes quantum mechanics at a fundamental level to sense, communicate, and process information in ways that are either practically prohibited or even impossible by conventional or classical means. Okay, so that's a general definition. And we'll talk primarily about computing today. And before we talk about quantum computing, let's remember classical computing from the last century. So if we go back to 1906, the vacuum tube was invented. It was a 3-terminal device used primarily for radios, amplification. It took a good 4 decades, so 40 years, before we found these vacuum tubes in a computer that's called ENIAC. That's shown right here. You've probably heard of that one. It's the Electronic Numerical Integrator and Computer. And you can see that it takes up a whole room. This is a person sitting here, crouched down, I think, doing some work on it. Not very powerful, but revolutionary at the time. Now, the next year, the transistor was invented at Bell Laboratories. You can see it here. It's maybe almost the size of your fist. And within about 10 years, we had a fully transistor-based computer called TX0 or TIXO. That was developed here at MIT. You can see it still takes up the better part of a room, although now there's a terminal and a chair you can sit at to program it. But it didn't look anything like the computers we have today, in the sense that the transistors were basically soldered together, discrete elements. They weren't integrated. To get to that, of course, we needed the integrated circuit in the late 50s, but it still wasn't until the 70s that we had chips where you would say, okay, yeah, that's an integrated circuit. This one is the Intel 4004, a 4-bit processor with only 2,000 transistors. 25 years later, we had the Pentium Pro. I remember using that computer, which was a chip with 5 million transistors. And then you'd still have to fast forward another 25, 30 years to get to where we are today, where we have multi-core processors, graphical processing units, billions of transistors, even approaching 100 billion on a single chip or set of chips. And from this vantage point, looking back, to get to these wonderful computers we have today, it took over 100 years of development. Now, we can compare with that quantum computing, which is, of course, much newer and nascent. Quantum computing started roughly in the 1980s when people like Richard Feynman, shown here, Uli Mann, and others suggested that, look, if you want to simulate a quantum system, you should use another quantum system to do that because, those are hard problems on classical computers. But getting from that initial concept to algorithms, that took a good 15 years. And some of the algorithms, which we'll go through, for example, Shor's factoring algorithm, Grover's algorithm, adiabatic quantum computing, and others, they started to come about in the mid-90s, along with quantum error correction. This was all theory. To get to reality and practical usage, of course, we needed hardware. And that hardware developed over the last 25, 30 years. And where we are today is that we have, small scale quantum computers, 100 qubits or so. Some of them are available in the cloud. You can use them and program them. And even the first demonstrations of quantum error correction. So what's the takeaway? Well, we can define the difference now between quantum 1.0 and 2.0. Quantum 1.0 is what we had in the last century. Basically, in the 1920s, many of our physics heroes developed quantum mechanics, and it helped us understand materials like, for example, semiconductors. And from that, we developed really useful devices like the transistor or the laser. But those are manifestly classical devices. A transistor is just a switch. It's an on-off switch. So we needed quantum mechanics to understand the semiconductors so we could build that classical switch. But at the end of the day, the computers we're using today, classical computers, are based on classical switches. That's quantum 1.0. Quantum 2.0 is, in fact, now using the quantum mechanics to make a better switch, right? Not just to understand the materials behind it, but actually the switching behavior is quantum mechanical. And it holds promise to have impact in this century. And maybe the third takeaway is that advancing from a discovery to a useful machine, it takes time and it takes engineering. Good. And many of you will help us do this. One slide on the types of qubits, fundamental logic elements that we have in our quantum computers. And they basically fall into two camps. One camp are the natural atoms, which appear in this periodic table here. And as you know, depending on the number of protons, neutrons, and electrons that form these atoms, you will get different elements with vastly different properties. Okay, and some of these elements can be used for quantum computing. Now, the other type are called artificial atoms. And these are basically circuits that we build. And you could think of it as, okay, using inductors, capacitors, and things called Josephson junctions, we can assemble circuits which in many ways behave like atoms. Okay, they have certain quantum mechanical properties that we can use. And in fact, you could even form a Mendeleev-like table of different circuits. This isn't complete, but there are many more than this. Where these all have different properties because they have different inductors, capacitors, and Josephson junctions. So quantum technologies are based on either natural atoms or artificial atoms, circuits, that mimic those properties. Okay. So how is a quantum computer different than a classical computer? Well, let's remember, okay, classical computers, they're based on bits. A classical bit is, say, the voltage, the presence or absence of a voltage on a transistor. And we assign that a state 0 or a state 1. Now, these are discrete states. Transistors are almost perfect. And so if we set that transistor in state 1, we'll measure it as state 1. Set it in 0, we'll measure it in state 0. Quantum computers, or qubits, are the quantum bits that form a quantum computer, are also two-state system, but they're quantum mechanical. And we think of it on something called the block sphere, or you can think of it as the planet Earth, where the North Pole is state 0 and the South Pole is state 1. Now, if you're at the North or the South Pole, you're just one of these classical bits. And so a qubit can be and represent a classical bit of information. But you need not, as a qubit, you need not only be at the North or South Pole. You could be anywhere on the surface of the block sphere. And when you're anywhere other than the North or South Pole, you're in a quantum superposition state of 0 and 1 simultaneously, with weighting coefficients that we call probability amplitudes, here shown as alpha and beta. Now, if you're on the equator, you're in an equal superposition of both 0 and 1 simultaneously. And one interesting consequence of these superposition states is that measurement becomes probabilistic. And so if you're on the equator and we make a measurement randomly with a 50% chance, you'll immediately snap to the North Pole, state 0, or you'll immediately snap to the South Pole, state 1. And it's 50-50. It's like flipping a coin. And you could go back to the equator at the same point and do the measurement again, and it will be, again, completely random whether you go to the North or South Pole. So what this means is that quantum computers rely on encoding information in fundamentally different ways than classical computers. So what's a consequence of this? Well, again, if we think of our classical computers, transistors, and we have n of those bits, we can actually form an exponentially large number of states from them, 2 to the nth power. But we can only represent one of them at a time. So let's take 3 transistors. We know we could set all of those transistors in state 0. We could set all of them in state 1, and all of the different permutations in between. There are 8 of them because 2 to the 3rd power is 8. Now, let's imagine that we wanted to compute a function given all of the different inputs. What are our choices? Well, we have an exponentially large number of them, so we really only have 2 choices. We could buy one computer and then one at a time feed in the inputs and get the outputs, or we could buy a large number of computers and run them in parallel. But either way, with an exponentially large number of inputs, it's going to take exponential time or exponential hardware. Now, quantum computers, on the other hand, we have n qubits, and there are still 2 to the n different states, classical states that can be formed from them. But we can combine all of those classical states into a single superposition state with these weighting coefficients now represented by alpha, beta, all the way up to gamma. And the important thing to remember, this is a single state, but it carries aspects of all of those classical states with weighting coefficients. And this leads to a quantum version of parallelism and, importantly, quantum interference, which together can effectively, in this cartoon, take an equal or an input superposition state, and it will output a superposition state. Now, when we make a measurement, we're going to collapse that down, and we'll talk about that in a moment. So how do we take advantage of this? Well, we take advantage of it by making algorithms. As we talked about at the beginning, many of these algorithms were developed in the mid-90s and continues on today. I won't read through the whole slide, but what we have on the left are the categories of algorithm, the classical time, how long it would take a classical computer to compute, say, a problem of a size represented by n, and then the quantum time, which indicates some speed up, and also there's still limitations. We're still doing research to make these better. Now, generally speaking, the classical time will have this n upstairs in the exponent, but the quantum time will bring it downstairs, and that's called an exponential improvement. Not all of these algorithms have it, but many do. And the types of algorithms that we're talking about are simulating quantum systems, quantum chemistry, pharmaceuticals, materials. Also, number theoretic algorithms like factoring, period finding. This is the algorithm that Peter Shor came up with and is behind Shor's algorithm, which compromises RSA cryptosystems. Solving systems of linear equations, AX equals B, linear algebra. We do this all the time. Optimization problems. Optimization is ubiquitous. Everybody's trying to optimize something. You'll notice here that that goes from 2 to the n to a question mark. And that's because optimization problems are characterized by the type or the quality of answer that you need. So for example, do we need the exact optimal solution, or is a high quality solution good enough? If I'm driving home from MIT to my home, and I'm using Google or Waze to do it, I probably don't need the optimal solution. Any one that gets me home within 5 or 10 minutes, if it takes me an hour, they're all good enough. And because of that ambiguity, this improvement is listed here as a question mark. And then finally, search algorithms like Grover's algorithm, we know provide a quadratic speed up. And listed here at the bottom, I should have mentioned, are many of my colleagues here at MIT who've really made this happen. So what does it take to achieve quantum advantage? Well, first, there should be no fast classical algorithm. The computers we're using right now are fantastic. And if we have a fast classical algorithm that's efficient, we should just use it. Now, there are lots of hard problems on a classical computer that we don't know a quantum algorithm, right? And so we need, of course, also to have a fast quantum algorithm. And then lastly, ideally, it should be a useful problem, which means, ultimately it could lead to, say, commercialization. And this overlap of these three, this Venn diagram, today is relatively small. And we, as a community, we want to make it bigger. And I challenge many of you to work on increasing the size of this overlap. And where this overlap occurs, we find that there are basically two types of quantum advantage represented by this formula here. And basically, what we're saying is that the size of the system we need to do this computation, or the time until we get a solution, or maybe the energy required to get that solution, is proportional to a function of n, where n is the number of qubits representative of the size, and then an exponential where n is now upstairs. Now, some quantum algorithms, like Grover's algorithm, will improve this polynomial function or the prefactor, and we call this a polynomial improvement as a result. One example would be if n goes to square root of n, like in Grover's algorithm, a quadratic speedup. This is better. Better is always good, but it's not as powerful as an exponential speedup, which we show here. And an example here would be that n upstairs in the exponent comes downstairs. So an exponential function of n becomes a polynomial function of n. And that is a fantastic improvement, unbelievably fantastic. It's exponential. And we certainly seek these types of algorithms. Now, we don't experience exponential growth every day in our lives around us. And so you may have heard this, but let me go through this exercise here. And in this exercise, over the next month, your boss or your parents or whatever say to you, hey, look, this month we're going to pay you in pennies, and here's how the game works. On the first day, we're going to give you 2 to the first power pennies. And on the second day, we'll give you 2 to the second power pennies. That's 4. And on the third day, 2 to the third, 8 pennies, etc. And at the end of the month, after 31 days, would you rather take all of the pennies or $10 million? And you think, okay, well, if you're like me, you go, okay, 2, 4, 6, 8, 16, 32, 64. Oh, wow. I've already gone through one of the 4 weeks this month, and I only have 64 cents. I think I will take the $10 million. But unfortunately, if you did that, you would have lost a large amount of money, because even just the 31st day, just the pennies on the 31st day are about $21 million, right? And this is the power of exponential growth. It just defies our common sense. Another way to look at it is you could ask the question, how large a classical computer would I need? And importantly, how much memory in that classical computer would I need to simulate a quantum computer and the calculation that it's doing in a brute force sense? Remember that there is a superposition state with lots of coefficients, and I need a large memory to keep track of that exponentially large number of coefficients. Now, if I'm simulating 30 qubits, I can do that on a laptop. I probably have enough memory on a powerful laptop to do that. If I increase that only by 20 more qubits, now I'm at 50. Now I need the memory of a supercomputer, maybe one of the top 10 supercomputers in the world. If I go to 80 qubits, now I basically need somehow all of the computers on the planet Earth network together and leverage all of their memory. Go to 160 qubits, and now we're in fantasy land. I need to somehow get all of the silicon atoms on Earth and employ them to be, each one is a memory element. And now I go to 300 qubits, just a factor 10 larger than where we started. And now I need all of the atoms in the known universe, each one representing a bit of information on my classical computer to store this. So clearly, this is a very, very large amount of information. Okay, so sounds great. Why don't we have quantum computers right now? And it comes down basically to 2 time scales. We call them coherence time and gate time. The coherence time is basically how long a qubit remains quantum mechanical. And it can be due to the environment or the control system, but it's how long does it retain its quantum nature. I can take my quantum computer and put it into a known state at time t equals 0. Let's call it psi. And from that point forward, immediately it starts interacting with its environment. That could be environment of its, say, substrate that it's on, or the environment of the control lines that are coming in, all of the environment, everything. And over time, that state will blur and eventually become lost. Now, the qubits are still there. They're not gone. But the point is that as I try to run an algorithm, I'm trying to take the state in a state space from point A to point B, but I'm fighting against the environment, which is also driving the qubit, and taking it to a different place C, which I don't know. Okay. Now, the time frame over which that happens is called the coherence time. Now, the second time scale we care about is the gate time. That's the time required for a single operation, a gate operation, which we use to implement algorithms. You know, they're not necessarily all the same, but take the slowest one or take the average one, doesn't really matter. And the figure of merit is how many gates can I apply within the coherence time that I have? And this is a proxy. The rigorous metric is called gate fidelity. Now, I want to mention that long coherence times, while good, are not sufficient. And what really matters is the number of gates before an error. And it turns out that long coherence times in systems are often associated with long gate times, so that when you take this ratio, it doesn't change that much. And I'll show that now on the next slide. So here's an example of different qubit modalities, candidates for qubits. And on the left axis is this metric, the number of operations before an error, how many gates within the coherence time. And that's basically 1-to-1 in the gate fidelity, shown here on the right. So if I have one error out of 100 gates, then I have 99% fidelity. One error in 1,000, 3 nines. And you can keep counting the nines. And you want as many nines as you can get. Now, the horizontal axis is the speed with which I can apply these gates, so 1 over the gate time. You can think of that as the clock rate in your conventional computer. And of course, faster is always better, so the best performance is in the upper right corner. Now, when we implement algorithms, we generally require 2 types of gates, single qubit gates and 2 qubit gates. And so what I've plotted here for these different technologies is the fidelity that they have for the different types of gates, the single qubit and the 2 qubit gates. This is just roughly speaking. And what you can see is that these different technologies appear in different places. So some of the leaders today are trapped ions. And here are some of my colleagues at MIT working on trapped ions. You can see that their single qubit fidelity is quite good. They'd like to make a better 2 qubit fidelity. And overall, both of them, they'd like to make faster. I work on superconducting qubits. Here are some of my colleagues too. And we have pretty fast qubits. We're basically trying to make them better. Now, in addition, neutral atoms, they're up and coming. And some of my colleagues at MIT working on neutral atoms. Also NV centers, that's nitrogen vacancy centers in diamond or other defect centers, and some of my colleagues. And I'm also starting to work on silicon quantum dots. I'm just telling you about the people here at MIT working on this. Of course, there are researchers worldwide working on these and related technologies. Okay, so this is what quantum computers look like today. In the lower left is a superconducting quantum computer from IBM. I think this one has about 400 qubits. In the upper left is Google's Sycamore processor. This one had 54 qubits, and they have larger processors now. This is also superconducting. In the upper middle is a neutral atom quantum computer, and it's hidden somewhat behind this door here. This is from Quera, and you can see a lot of optics in there. It's based on optics and runs neutral atoms. The IonQ quantum computer in the upper right, this is a trapped ion quantum computer. It's also hidden inside a black box, but it is also using lasers and traps that hold the ions. And in the lower right is a D-wave quantum computer, which in this black box has a large refrigerator and quantum annealing. And of course, in the lower part here, you'll recognize this. This is not obviously a quantum computer. This is the Wright flyer. And I put this picture here because I think it's representative of where we are in the field of quantum computing today. This Wright flyer was not the first time that humankind flew. People had hot air balloons, people flew in gliders before this event, but this was the point where it all came together, that we had a control system and a person boarded that plane, was able to steer it, it was under its own propulsion, and it flew. Didn't fly very far, not very far off the ground either, but when we saw this event, we knew that commercial aviation would come. It would take a couple decades, but it would come. And I believe that we have had this Wright brothers moment now for quantum computing. So to realize the promise of quantum computers, we need to engineer systems that are robust, reproducible, and extensible. And in a sense, we need to make these quantum computers larger. Okay, so in order to do that, we need something called error correction. And let me just describe this at a high level. The physical qubits we have today, those are the qubits we've been talking about. Me and my colleagues and others, we've worked really hard to get the error rates down, 1 part in, say, 10 to the 4, right? You could ask, where do we need to be for commercial applications? We actually need to be down here in the blue region, 1 in a billion or 1 in a trillion. And you might think, oh, wow, that's a giant chasm, and it is. How are we going to get there? I'll just mention here that transistors are really fantastic. Classical transistors have an error rate of 1 part better than 10 to the 20. They almost never fail. Fortunately, we don't need to be that good. We just need to be in this blue region. But there's a big chasm here, and the question is, how are we going to do it? We probably are not going to be able to make the physical qubits each 6, 9 orders of magnitude better. Rather, what we're going to do is called error correction. And the idea is that we're going to take physical qubits and we're going to make a team out of them. We're going to aggregate a larger number of those together, and this team of physical qubits, which we call a logical qubit, will together act like a single superqubit with a much better performance. So that's the promise of error correction. And if you look at the error per cycle of this logical qubit, you'll see that it comes with 2 factors. One is a prefactor, which is basically a penalty. If I form a team with lots of people or with lots of qubits, I need to do more things to take care of them and operate them. So that actually works against me. But we know that if we form teams, often with these teams, we can do so much more than any of the individuals could do themselves. And in this error correction language, that turns out to be an exponential improvement. So we pay a penalty, but we get exponential improvement. And you can see this exponential improvement as you increase the size of the team, something that we call distance in error correction language. So if you have a 3 by 3 array of these qubits, that's distance 3, you can go to a 5 by 5 array, and now you'll get exponential improvement. Now you may notice that there are some blue qubits there as well. They're basically checker qubits. They're the ones who tell us when and where an error occurs, and based on that, we can go in and then correct for those errors. So again, exponential improvement, what does that look like? Well, on this horizontal axis, we're looking at the physical error rate of our, say, 2-qubit gates. And these are at, say, the 0.1% level. And then we look at the logical team, the logical error rate for different size teams. And you can see as we go from a distance 3 with 17 qubits up to a distance, say, 17 or 25 with 1,000 qubits, that the error rate is improving by orders and orders of magnitude, all right? In fact, well below 10 to minus 6, you can see that the distance 17 and red and the purple distance 25, they're going to be down here at 10 to minus 9, 10 to minus 12. So Google Quantum AI, from whom I borrowed this slide, they've demonstrated improved performance going from distance 3 to distance 5. And there have been also demonstrations of error correction from other researchers worldwide at Zurich, Innsbruck, Quantinuum, USTC, and IBM. So we're really at the verge of doing this, but this is so important to achieving commercial quantum computing at scale. So I just want to give in the last few minutes an intuition for what this error correction involves. So what I've shown here is a layered architecture, computing architecture. The algorithm or the application is at the top. The physical qubits are at the bottom. And then in the middle, you can see things that you might recognize, like a logical controller, which interprets your algorithm and decides what pulses I need to apply. And in the middle, we have two sections, passive and active quantum error correction. And on every clock cycle of our computer, basically the logical controller needs to do a few things. Of course, it needs to run the algorithm, so it's throwing those pulses at the physical qubits, but it's also doing error detection, error mitigation, and then error correction. So what do these look like? I like to talk about this in the context of Lacrosse to give a physical intuition for what's going on. And let's start with the physical qubits. So this young man here, he's a physical qubit, and he's trying to hold the ball in his lacrosse stick. If you're familiar with lacrosse, you want to carry the ball in the basket of your stick and then go to the opponent's goal and score. And this person was rather unhappy when I asked him to do this because I said, play lacrosse like you would never do. And basically what you see is he's running, and the very act of him running creates noise. And in fact, the ground is also not perfectly smooth. That's also noisy. And so when he runs, basically the ball falls out very quickly. And you can think of that as decoherence in our physical qubits. There are errors that occur very rapidly. So of course, we don't do that. What we do as lacrosse players is something called cradling. And this is an example of passive error suppression. It's something that we just do without thinking about it, and it usually works. And what you can see is that by cradling the ball back and forth 180 degrees left and right, that the player is still running and he's still running on uneven ground, but all of that noise, well, not all of it, much of that noise is decoupled from his lacrosse basket. And so the ball stays in the basket and he can run down and score. This is called passive error suppression. Doesn't fix everything, but it does fix a lot. Of course, there's some left over, and we can only address that by active error correction. So of course, occasionally the defender will come up from behind, knock the ball out, and when that happens, the player has to actively detect that an error occurred. Oh, I dropped the ball, and then actively go over and pick it up. And that's active error correction. And you'll notice that when he picks the ball back up, he immediately starts back with layer 2, the passive error suppression. Here it comes. Now he starts cradling immediately again. Okay. So with that, this is my last slide. What is the reality of quantum computing today? There are a lot of myths out there. Let's just dispel with them now. So first off, quantum computers will not replace classical computers. First off, quantum computers don't solve efficiently every type of problem. They only solve certain problems efficiently. And so that's number one. Number two is that just operating a quantum computer and doing the error correction will need a classical computer in tandem. Okay, so quantum computers will work in tandem with classical computers. They will not replace them. Secondly, is we need more quantum algorithms. There are very few commercial algorithms that we know of today, and I encourage all of you to think about developing algorithms that, if you remember that Venn diagram, increase the space of algorithms on a quantum computer that address important commercial problems. Third is that very likely we're going to need quantum error correction to realize the full promise of quantum computing. Right now, we're working very hard, many of us, to do error correction. Other researchers are working hard to ask, what can we do before error correction? And we may find some applications that will be a bridge between now and the future when we have error correction. And both of those tasks are important. But for general purpose quantum computing, we very likely will need error correction. And then lastly, quantum computers will not break our encryption very soon with Shor's algorithm. RSA 2048-bit keys requires around 4,000 error-corrected qubits, but those are error-corrected. They're a team, and that team comprises many physical qubits. Today, it would maybe be around 1,000. So we're talking about at least 4 million qubits, and in fact, likely more. We're very far from that. On the other hand, we don't want to wait until that quantum computer is built because to change because we're encrypting information today that we want to remain secure in the future. And that's why we need to switch to what's called post-quantum encryption. And we need to do that now. NIST has been working on that for about 10 years. They're announcing, I believe, this year what that post-quantum crypto system will be. And it's something we believe very strongly will be immune to attack by a future quantum computer. You'll use this new post-quantum crypto on your classical computers. It's just a classical algorithm, but it's one that we believe will be immune to attack by a future quantum computer. And we need to switch over so we're encrypting information now so that when a quantum computer comes along, our information is still secure. With that, let me acknowledge many colleagues, including the Engineering Quantum Systems Group and our sister group out at MIT's Lincoln Laboratory. We have many US government sponsors and corporate sponsors that help us along with this and make it possible. And with that, I thank you for your attention.
Thank you very much, Will, for this really exciting and very insightful and informative lecture. I'm sure it is really helpful for everyone. I know that everyone is eagerly awaiting the lab tour, but we also have many questions. So I will quickly field a couple of questions to you, Will, before we go on with the virtual lab tour together with Will Oliver and Shantanu Jha. The first question, this Womanium program is focused eventually towards applications, and people will look into quantum for climate and energy, other use cases, what could be use cases where we could have quantum advantage fastest. Where do you see interesting application areas?
Yeah, that's a fantastic question. And as I said, we really are looking to you to help us develop these future quantum algorithms. In the near term, I believe that quantum algorithms will help us with simulating quantum systems. Those are materials, could be chemistries, pharmaceutical drugs would be one application. These will require large-scale quantum computers, but these are immediate applications. And it's a two-step. We use the quantum computer to emulate or simulate these new materials or chemistries, and then scientists and engineers will use that knowledge and apply it to new technologies like better batteries, for example, or better drugs. So that's how I see quantum computers being used initially. There's also promise in helping with optimization problems, as we talked about. I think that because of just the sheer amount of optimization that humankind needs to do, that it behooves us to find algorithms that can find advantage in optimization.
Then next question, how will classical computers, the ones we have, quantum computers, supercomputers, and AI, how will it join forces in the future?
Yeah, that's a great question. And I still think we're trying to figure that out. What's clear is that quantum computers and classical computers will absolutely need to work in tandem. We talked about doing that for quantum error correction. There's also an idea that in running an algorithm, that the classical computer may sit on top and run much of the algorithm, and then ask the quantum computer node or multiple nodes a simpler question or a specific question that the quantum computer is particularly good at answering, and it gives the answer back, and then the classical computer continues. And that type of coprocessor or accelerator by a quantum computer might be the first way that we see advantage in quantum computing.
Fantastic. We have more questions. Some of them we will ask during the Q&A of the virtual lab tour. Some others we will ask next week when we focus on quantum annealing and when we focus on hardware. And right now, Shantanu, are you online and can you turn on your video? Wonderful. I will spotlight you as well. And then it is time to, in addition to Will Oliver at MIT, also welcome Shantanu Jha from Will Oliver's group at MIT. Shantanu Jha is a PhD student working with Will Oliver, exploring bosonic systems for fault-tolerant quantum computation. I'm sure you will share more about that soon. And in addition to the research, he does a lot of quantum computing outreach. For example, has led the MIT QHack, founded Yale, the Yale undergrad quantum computing group, and is in addition the co-founder and CEO of Boston Quantum, a startup building physics-inspired algorithms for the financial industry. We are really excited now to show a virtual lab tour recorded by Shantanu and his colleagues in the lab of Will Oliver at MIT. I will share the screen. Fantastic. Thank you so much, Shantanu and Will, for this wonderful lab tour. I see many positive comments on Discord. Shirlene from UK says, I love the outro. Sujit from India says, it was amazing. Mohammed Ali from Iran adds, truly amazing. Lovely labs. That's fantastic. Thanks. Those dudes are so enjoying lab stuff. I think that's right. There were also some questions about the noise in the background of the video, which is unavoidable. Can you explain that a little more?
Yeah, maybe it's a little bit avoidable if we had used better audio tech, but this was filmed 2 years ago by grad students. I think we did a pretty good job. Some of that is from, like we said in the video, liquid helium pulsing through tubes, kind of similar to water sizzling on a hot pan, and other from fans from microwave electronics. Yeah.
And while Amir was showing all the electronics racks, there was a question from a participant whose name is also Amir. He asked, is this the quantum computer? But can you explain how actually many of the pieces in the video would make up a quantum computer together?
Yeah, sure. Yep. So the quantum computer itself is that chip that you saw in the fab, or one like that. And Aziza also showed a chip that you could look at on the screen from a microscope image. So that is what I would call the quantum computer. But to control the quantum computer, to make it do what we want, we need to send, in our case, electrical signals down to that chip. And all of that room temperature gear you saw was in service of sending down the right signals at the right times in order to make the qubits do what we want them to do. And then also to read out the states they ended up in so that we get the answer to some problem we were trying to solve.
And then could you also create the link, Will, what you shared about artificial atoms in your talk, and then now the chip that we saw. How is this superconducting qubit an artificial atom?
Yeah, so when we looked at that chip, Aziza mentioned that, oh, I've got 4 qubits here, 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 and here. And of course, it's probably hard to figure out what she was talking about exactly. But there were 4 qubits on that chip. And then there were 4 tunable couplers on that chip. And so when we talk about artificial atoms, we're talking about circuits built from inductors, capacitors, that you could see with your, with the help of a microscope. You could see those elements, and those elements, those qubits, behave like natural atoms in the periodic table, but they're much larger. Each one of those elements has Avogadro's numbers of atoms, right? But the circuit together behaves, like an artificial atom. And we can drive transitions in it just like you can drive transitions in an atom. It has quantum coherence just like a natural atom does. And of course, we make qubits from it just like we do from natural atoms.
I think that's super cool, by the way. Like when we think about atoms, we're talking about like 10 to the minus 10 meters, like angstroms. But these systems, which we can literally see with our naked eye, we're talking about like millimeter scale, right? Exhibit these quantum mechanical effects because we're able to, isolate them so well, cool them down so well. And like Will said, describe kind of the motion of many, many electrons with single degrees of freedom, or, countable small amount of degrees of freedom, which is, I think, very cool.
One of the, just one last thing on that is one of the coolest things I've run across in the last 30 years is that, you think about quantum mechanics that we learn in class, and that was used originally to describe the physics of electrons, neutrons, protons, atoms, really small things. Small things behave differently than big things, right? But what we're doing today is that same quantum mechanics, we're able to make it work at 100 microns or millimeter or even 5 millimeters, right? And so that same quantum mechanics works at large scales, not just at small scales when it was first developed for.
Yeah. Talking about those large scales, or a bit differently, in the video you showed 16 qubits. Now, Hussein Shiri from Lebanon asks that according to him, in the IBM roadmap, they plan to reach more than 1 billion gates in a superconducting quantum circuit. And he asks, is that even possible? How is that possible? And what could the disadvantages be?
Well, IBM certainly thinks it's possible, and I agree with them. We're going to be able to do that. I think the question is really over what time frame will it happen? And when we talk about 1 billion gates, we're talking about some number of qubits, which we call the circuit width. And then we talk about the gates in time that we apply to those qubits, and that's called the circuit depth. And if you multiply the width times the depth, they're saying, hey, we're going to get to 1 billion, right? And that's very ambitious, as it should be, but that's what we need if we're going to realize, commercial important benefits from quantum computers. And so, I'm cheering for them to be successful.
Yeah,
Fantastic.
a large part of this, as Will mentioned, as we mentioned in the tours, is error correction. And so in our group, for example, we have different projects that go towards this goal of having an error corrected or fault tolerant quantum computer. So we have some projects that are looking at many physical qubits brought together to create a more robust logical qubit. In my research, I work on, like I said, using a much larger space of a quantum harmonic oscillator, the ability to put 0 photons, 1 photon, 2 photon, 3 photon, and so on into this cavity to redundantly encode information in a way that we can correct errors. And that, in addition to kind of quantum engineering of gates and other control and materials and everything, is, I think, going to help us get to this fault tolerant quantum computer.
Yeah,
a lot of interesting problems. Yeah.
Very quick thing there. In the engineering quantum systems group at MIT, we focus on learning how to scale, right? We're not going to do the scaling. We're a university. That's not our lane, and it's not our job. But what our job is to figure out the ways, the engineering, the physics, the new techniques that we can use to scale, how to scale. And then companies like Google, IBM, AWS, and others hopefully will take those and actually do the scaling, and we'll be cheering for them.
Fantastic. There is also a question if you also work on theory, Will, or how the collaboration with theorists is.
Yeah, well, I do require myself and the students in the group that they need to understand the theory of what they are doing. And we do have 1 or 2 people who are more theoretically inclined than experimentally. But generally we're an experimental group, and we collaborate with many theorists, both at MIT and outside MIT, worldwide, in fact. Yeah.
Then there is a question from Izzy from the United States. Will room temperature quantum computers be possible at some point?
Oh, I think so. Now, probably not with superconducting qubits. But you think back in history, right? We started with vacuum tubes, and they were very big. And when the computers got up to, say, 10,000, 100,000 vacuum tubes, at some point they were failing too quickly. They had to be replaced all the time. We needed something new. And then we graduated to a bipolar junction transistor, and then eventually to emitter coupled logic, and then eventually to CMOS. Technology evolves over time. I certainly hope that in 50, 60 years, we're still not using dilution refrigerators to do quantum computing, but something at room temperature. So for example, neutral atoms and trapped ions in principle can run at room temperature, or integrated photonics often run at room temperature. Now, all of those technologies may elect to run at some level of cryogenic temperatures for some advantage today, but there is a pathway to get to room temperature quantum computing.
Maybe I can ask a question for you, Will. Do you think that these different platforms will kind of serve different purposes? Maybe one as a quantum memory, one as like a kind of a processor, and play well together in the future?
Maybe, yeah, especially in the early days when we're just trying to get the technology to stand up. It could be that many of these technologies are application specific. Superconductors are good at one thing, and semiconductors at another, and photonics at yet another thing. And so we'll find application specific needs for these different platforms. And then in some cases, the application may dictate that multiple platforms work together.
Fantastic. I would love to continue this for at least 30 minutes more, but we need to conclude soon. I would like to ask you, Shantanu, what do your days look like? Because you are a researcher in the lab. You founded Boston Quantum and many more things. Can you share a bit?
Yeah, I mean, my full-time job, my full-time passion is doing research in the group, so that's my day-to-day. But it depends on exactly what I'm doing. I would say in the day, or in the part of my research journey. For example, in the last year, I was doing a lot more theory, numerical simulation, and design of a device that I was designing. And just yesterday, we got those devices. So that was like Christmas morning when I saw those devices. And we're going to cool those down. If you remember in the lab tour, I was showing this larger kind of aluminum block. We replaced that with a fully 2D chip, a fully 2D architecture, which we think will be more extensible. We improved the sort of control circuit that we use to control information inside the quantum harmonic oscillator. And so now my day-to-day is going to be more, experiment focused, measurement focused. But it depends on what part of this stage we're at. Like Will said, we kind of do all things. We do theory, numerical simulation, design, experiment. Then we figure out, okay, what's wrong with the experiment, we iterate with collaborators, of course. Yeah.
I can't wait to hear the initial results. I'm looking forward to it.
Yeah, I can't wait.
Very exciting. And Will, what is your advice for new students wanting to enter the quantum field now? How should they approach this?
Well, I generally tell people do what you're passionate about. Quantum computing is becoming a more and more mature field over time. And what that means is that we need people from all walks of life. So not just the physics department, not just the EE department, but in fact, other departments like chemistry. They know hard problems that might be solved by a quantum computer. And so, what's more important is do what you're passionate about and then bring your skills to the table of what we're calling quantum computing. And of course, if your passion is in physics, do that, or electrical engineering. But just to say that the needs of this field have moved beyond just simple laboratory experiments and requires everything from cryogenics to fabrication engineering, material science, design, electronics, signal processing, and even in the business field, with all the commercialization that's starting to happen, we need people who actually know something about business and marketing to make this successful. So rather than saying, what should I do to be quantum? I would say do what you're passionate about and good at, and then bring those skills to quantum.
Wonderful. Will, Shantanu, thank you very much for this exciting keynote, this exciting virtual lab tour. I will share a couple more comments from the chat. Shantanu, also in Shantanu Baya says, coolest place on Earth and coolest place to be on Earth. There are many comments that people would love to visit physically, that I would like to join your lab, that I would like to come to MIT, and also many more questions that I didn't ask. But everyone, next week, Monday, there will be a lecture on quantum hardware by Dan Schlichter from NIST, where he will share about superconducting qubits, but also trapped ions, how photons are used. So there you can ask more. There will be more on quantum annealing. There will be more algorithms. So save those questions for there. Again, Will, Shantanu, thank you very much, and we will be in touch.
Sounds good. Thank you, and thanks for all the good work you're doing, Marlou and team.
Thank you both.
Yeah, likewise. Thanks so much.
See you.
And now it's time for a brief break. Let's take a break of 3 minutes, and then we will enter the second part of this session, Grover's algorithm. And Will Oliver actually mentioned Grover's algorithm as one of the well-known algorithms. Today you will learn how it works. For the new people, during this break, I will share a little bit about the platforms, where can you find the schedule, what is coming up next week. But everyone, this is the time to take some drink, turn off your brain for 2 minutes before we delve in depth. And thank you all for these really great questions.